Hello mathematicians, we're now going to have a look at sum and product of roots. Now while this is a smallish area in the advanced mathematics course, it becomes more significant when we do polynomials in extension 1 and in extension 2. So the concept is reasonable enough. If a quadratic equation has two roots, alpha and beta, which we know are the values that make the quadratic equation equal 0, then it has factors, x minus alpha and x minus beta. And the simplest quadratic with these factors is obtained by just multiplying them together. So this would give us the monic quadratic, which is that, if we expanded those brackets out. Now if we just extend that idea a little bit, so for any quadratic equation with values a, b and c, coefficients a, b and c, which we could write as x squared plus b on a x plus c on a equals 0 by dividing right through by a. If our quadratic equation has roots alpha and beta, then we can see that the sum of the roots, which is what this is, alpha plus beta, must equal minus b on a. And likewise the product of the roots, which is what this is, equals c on a. Now that's the part that we just have to know automatically for this, and the exercises in 2 unit are generally of the type shown below here. So if we have our quadratic equation 2x squared minus 6x minus 1 equals 0, we can see a, b is minus 6 and c is minus 1. So alpha plus beta, the sum of the roots. Now occasionally I'll slip into saying the sum of the roots 1 at a time and 2 at a time and so on. That will make more sense down the track, so just bear with me for that. So the sum of the roots alpha plus beta is minus b over a. So that equals minus 6 over 2, which is plus 6 over 2, which is 3. So whatever the roots are, and we don't know what they are, we haven't found what they are, we could. We haven't found what they are, but we do know that they add to 3. And we do know that they multiply together to give us whatever c on a is, which is minus 1 on 2. Now obviously this is the basis for our product and sum method that we used, well, way back in junior school to be able to factorize a quadratic. So the product and sum bit is because of this relationship here. Now, when we get to these sorts of things, as soon as we move away from alpha plus beta or alpha beta, then unless we actually know the value of alpha and know the value of beta, which is usually discouraged, then we have to work on this algebraically to make it some combination of these. So this just becomes a little algebra puzzle at this stage. So knowing our building blocks, basically, we want to see how this is constructed from those building blocks. So for example, this first one here, we could see our algebra instincts tell us that we could take out alpha beta as a common factor, and that will leave alpha plus beta. And we know the value for each of those. So alpha beta is minus a half, alpha plus beta is 3, so we've got minus 3 on 2 as this expression here. 1 on alpha plus 1 on beta, your algebra instincts say get a common denominator, so we get that, and we know that that is then going to be 3 over minus a half, which will become minus 6. And this one here, alpha squared plus beta squared, I think if you remember the example we were working on yesterday in an unrelated area, then the thing is that if I have alpha plus beta all squared, we know that that's alpha squared plus 2 alpha beta plus beta squared. So alpha squared plus beta squared then is going to equal alpha plus beta, which we know, all squared, minus 2 alpha beta, which we know. So alpha plus beta squared is going to be 3 squared minus 2 times minus a half. So that will give us 9 plus 1, which is 10. Now, let's look at this one. The first part is a proof. So as per usual, if we set this proof out by taking one side, usually the most complex looking one, and show that it equals the other side. So if we have alpha plus beta all squared minus 4 alpha beta, then if I expand this, square of the first twice their product plus the square of the second minus 4 alpha beta, you can see that that will become alpha squared minus 2 alpha beta plus beta squared when we gather terms, which is alpha minus beta all squared, which is our right hand side. And for B, part 1, for this particular quadratic with zeros alpha and beta, we're going to use our result from part 1 to find initially what alpha minus beta all squared is. So alpha minus beta all squared is, of course, from above, alpha plus beta all squared minus 4 alpha beta. Alpha plus beta is minus b over a, so that's minus 9 over 1. So that's plus 9 squared minus 4 times alpha beta, and alpha beta is c over a, which is 2 over 1, which is 2. So it becomes 81 minus 8, which is then 73. Now, part 2 just has a useful little trick in it. Probably more so for extension 2 than extension 1, but it's worth understanding. So suppose I wanted the absolute value of alpha minus beta. Then we know that our answer is always going to turn out to be positive, and it's really the difference in size between alpha and beta. But we also know that without knowing the size of them, we really should go through 2 cases and so on. So I'm going to introduce a little trick. And the little trick is that the first thing I'm going to do is that I'll take my alpha minus beta and I'll square it. Because when I square it, no matter what the difference is, no matter which one is bigger, my answer is going to be positive. And then I'm going to undo the square by taking the square root, and if I just write the square root without plus or minus in front of it, I'm just getting the positive answer. So alpha minus beta squared was 73, we found from up above, so I want the square root of 73 as my answer for this. Now for my next example, I want to find a value of m which will ensure that one of the roots of this equation is twice the other, but without obviously finding the roots, because I can't now. I don't have the value of m. So what is this telling me? If one root is twice the other, well, let's let one root be alpha, and therefore the other root is twice alpha. So if that's the case, then what have we got? We've got the fact that the sum of the roots, so therefore alpha plus beta is alpha plus 2 alpha, which is 3 alpha, and the product of the roots, alpha beta, is alpha times 2 alpha, which is 2 alpha squared. So we also know that we can write down an expression for alpha plus beta and for alpha beta from our equation up here. So therefore 3 alpha, alpha plus beta is minus b over a, so that's minus m, and alpha beta, which is 2 alpha squared, is c over a, which is 18. So you can see then, and I'm sure you knew why I was writing the 1 and the 2, because we've got 2 unknowns and therefore we're going to have 2 equations. We're going to solve them simultaneously. Now we don't actually want to know the value of alpha. We can work it out if we wish. We want to know the value of m for this question. So when we're solving these equations, just a little bit of cleverness or laziness, whichever way you look at it, is that the variable I'm going to eliminate is alpha. So from one of these equations, and it's probably easiest from equation 1, so from equation 1, if I get an expression for alpha, that's minus m on 3, and I put that into equation 2, and I'll have 2 times alpha squared, so that's 2 times minus m on 3 squared, which will become m squared on 9, the negatives have gone, that equals 18. And now I solve this. So if I divide the 2 over, that will give me 9, multiply the 9 across, that will give me 81. So m squared equals 81, m equals plus or minus 9. So have a go at these ones out of 8H. I can't remember why I asterisked 11. Presumably it's hard. So enjoy.